The Industrial Revolution has changed many of man's ways of living and opened wide the door of opportunity for vast new achievements. But we of the 20th century are experiencing an even greater revolution based on atomic radiation. Atomic radiation is leading to new achievements in all facets of human activity. In medicine, atomic radiation makes possible new techniques of diagnosis and treatment. In industry, atomic radiation leads to new procedures and time-saving shortcuts. For historians and others, atomic radiation provides a new means of measuring the age of ancient objects. For agriculture, atomic radiation has provided new tools with which to study living processes. This atomic radiation that is leading to so many new and useful developments is energy released by radioactive atoms. The discovery of this kind of energy was made more than half a century ago by the French chemist and physicist Henri Becquerel. In one experiment, he planned to expose uranium to strong sunlight, but cloudy skies forced him to postpone his first attempt. His plan was simple. He had wrapped an unexposed photographic plate in black paper. Outside the paper, he had placed uranium crystals. He believed that sunlight would activate the uranium and cause it to release rays somewhat like X-rays, rays that would expose the photographic plate right through the paper. Because of the cloudy day, he laid aside the plate temporarily. Sometime later, Becquerel's assistant, by chance, developed the photographic plate. He was amazed to find that it showed signs of exposure. The explanation is simple. Uranium, being naturally radioactive, continually gives off radiations in darkness or in light. Some of these radiations had penetrated the paper and exposed the photographic plate. Becquerel was quick to realize that the exposure was the result of some special property of the uranium, a property he named radioactivity. The secrets of radioactivity lie within the atoms. Atoms themselves are units of matter so small that it takes billions and billions of them to make a speck of dust. And yet, each of these atoms is made up of parts infinitesimally smaller than the whole. Many of these parts are present in the center, or nucleus of the atom. Because radiations come from the nuclei of atoms, scientists usually speak of nuclear radiation rather than atomic radiation. A number of different radiations have been discovered. The nature of some of them, such as alpha, beta, and gamma radiations, is particularly well known. An alpha radiation consists of two smaller positive particles called protons and two others called neutrons, each consisting of one positive and one negative particle. A beta particle is a single negative particle which has escaped from a nucleus and is identical with the electrons we encounter in ordinary electrical measurements. Gamma rays resemble X-rays and light waves, but they are more energetic and penetrating. What are some of the principal properties of these atomic radiations? Among the first investigators to study the properties of atomic radiations were the famed Curie, Pierre and Marie, the discoverers of radium. The Curies investigated the three kinds of radiation released by radium. As Pierre explained,
a piece of radium is placed within a lead block, a strong magnetic field, and a photographic plate above the opening. Any radiations escaping through this opening pass through the magnetic field before reaching the photographic plate.
And in a darkened place with a suitable vacuum, the plate is exposed and we take a picture of the radiation.
Something like the kind my teacher, Professor Becquerel, got accidentally some years ago.
That is true. And the exposure results in the same pattern each time the experiment is made. Here are the tracks left by what Ernest Rutherford calls the alpha particles. They appear to go to one side of the magnetic field. And here are the tracks of the beta particles. They go in the opposite direction of the magnetic field. and a slight darkening in the center shows the path of the gamma rays.
As Pierre Curie had discovered, beta particles are attracted to the positive pole, proving that they are negatively charged since unlike charges attract. Alpha particles are attracted to the negative pole, proving that they are positive. And gamma rays do not behave like charged particles. That is, they are not deflected toward either pole. Extensive studies of atomic nuclei by the Curies and others quickly created a desire to invent pictures representing atoms and their nuclei. It's as a teacher explains to his class in beginning science.
This isn't the most accurate picture, but in medicine, in agriculture, in industry, and in the arts of war, it works. It isn't the only kind of picture we could draw. There actually is no one picture that tells the whole story. But it is an easy one to understand, and it helps to keep our thinking clear about things we can't see. The atom can be compared in a rough way to our solar system. Electrons move around in their orbits, much like the Earth and the other planets revolve around our sun. Within every atom is a core called the nucleus. It's the nucleus that we're really after in our study of radioactivity. Every nucleus is made up of a bundle of particles bound together by forces of immense magnitude. If the balance of these forces in the nucleus is sufficiently disturbed, some of the nuclear particles are thrown off.
Each time a change takes place in a nucleus, that nucleus loses part of its mass as radioactive energy. In the case of uranium, the end product is the stable element lead. No further decay or change in the lead atoms takes place. Uranium-235 can split apart or fission. The splitting or fissioning starts whenever a neutron enters its nucleus. In addition to the new atoms produced, 2 or 3 extra neutrons are liberated. In turn, each of these neutrons is capable of splitting another atom. So if there is plenty of uranium-235, one neutron can, at the very least, release 2 neutrons. The 2 can release 4. The 4, 8. The 8, 16. And so on. Since neutrons are present in the atmosphere, and since there are billions of atoms ready to explode in a radioactive mass no larger than a pinhead, we can anticipate what will happen when a large enough amount of uranium-235 is assembled at one place at one instant of time. Such nuclear fissioning can be controlled. In nuclear reactors like this one, the fissioning reaction is taking place, but it's taking place on a much smaller scale than in the bomb. Inside this reactor, some of the neutrons that are being released are permitted to hit targets made of ordinary stable elements like copper or iodine, cobalt or calcium. When this happens, the stable elements change into radioactive elements. These artificially produced radioactive elements are called radioisotopes. And it is these radioisotopes that are proving so valuable in different facets of human life. Atomic radiations of any kind may prove damaging to human beings. So techniques of protecting those who work with such radiations have had to be perfected. Special equipment and different kinds of protective barriers are some of the measures that have been adopted to safeguard humans. Inventing instruments to detect radiations and discovering materials that will block and stop radiations require extensive tests. Here is an example of an experiment in which a Geiger counter and scaler are used. To begin with, here is a common source of alpha radiation in the substance called polonium or radium-M. The clicking sound indicates that radiations are being released by the polonium. Alpha particle radiations are relatively slow-moving. An ordinary sheet of paper stops them, so the clicking sounds diminish. Here is a sample of radium-E. It releases beta particles. Beta particles are lighter and faster than alpha particles, and they pass through the paper barrier. This aluminum plate stops them. Here is a sample of cobalt-60. It releases gamma rays. Gamma rays travel at the speed of light and pass through paper and aluminum, but a half-inch piece of lead stops them. We can summarize the experiment with this drawing. Paper stops the alpha rays, aluminum stops the beta rays, and lead stops the gamma rays. Our understanding of atomic radiation has been greatly increased since Becquerel's discovery in 1896. We know of three kinds of radioactivity: cosmic, from outer space; natural, from elements like radium; and artificial, produced when stable elements are bombarded by neutrons. Atomic radiation is proving to be one of the most useful discoveries ever made. The effects of these radiations on living things, the means we have of producing radioisotopes, the techniques we have to protect ourselves from radiation injury, are but a few of the directions in which research has led us in the study of atomic radiation. And all the while, our leaders in research and invention are making new discoveries that continue to multiply the uses of the radiation for the benefit of all mankind.